Our last little section over section 16.8 is to look at problem number 19 in the exercises at the end of section 16.8. And in this problem, we are asked to show that if S is a sphere and F is a vector field that satisfies the hypotheses of Stokes' theorem, then the double integral over S of the curl of F dot ds is equal to 0. Now, usually, if you're asked to show that something is the case about the curl of a vector field over some surface, and you're asked to use Stokes' theorem, then you would go and find the boundary curve C and evaluate the integral along C of f dot dr. But a sphere has no such boundary curve. It has a boundary, and but it's a closed surface, so it doesn't have an edge the way that we've been working with. So this solution here is going to take some creativity, and really what we have to do is divide up the sphere into, and doesn't have to be upper and lower, but I'm going to say an upper and a lower hemisphere, I guess. Divide up the sphere into, how about, let's say, upper and lower hemispheres. So in other words, S, the sphere, will be S1 union S2. And now I have to draw this a little bit. Whoops. Where S1 is, say, the upper hemisphere. And let's come down here. So I guess I need to do like this. And S2 is the lower hemisphere. So I've divided it up and separated them a little bit. Now, C is, each of them then has a boundary curve C, and it's the same set of points, even though I've separated them a little bit, right? So let's see. Now we're not given whether we think in terms of outward or inward orientation here, but it turns out that won't matter. So let's use outward orientation. So normal vector like that. Now, if you rotate that normal vector around here, down here, outward orientation is like this. So again, and we know, we've seen what that vector is for a sphere, but we don't need the details. All we really need is that now for this curve C here, For the upper hemisphere, we have to go around C like this. And if our head was oriented upwards, in order to keep the hemisphere on our left, we would have to go around C like so. If you're standing upside down here, and you want to keep C on your left, I'm sorry, you want to keep S2 on your left. So then you have to go in the opposite direction. So here, in order to keep S1 on your left, you have to go around like this. In order to keep S2 on your left, you have to go around in the opposite way. But like I said, so let's call this C1 and let's call this C2. And the key point is that C1 is equal to minus C2, or you could say C2 is minus C1. They're the same curve, just with opposite directions. So the double integral over S of the curl of f dot ds must be equal to the double integral over S1 of the curl of f dot ds1. I'm running out of room here. Plus the double integral over S2 of the curl of f dot ds2. And then we can apply Stokes' theorem to each of these situations here, because since the assumptions were met for the whole sphere, they're going to be met for each hemisphere. And so the first one is then the line integral along C1 of f dot dr. The second one is the line integral along C2 of f dot dr. But since C2 is minus C1, remember it's work integrals like this that since the tangent vectors are going to be reversed, these are going to be, this is just going to be minus the integral along C1 of f dot dr. I mean, really it's plus the integral along minus C1 of f dot dr, which is minus the integral along C1 of f dot dr, which is 0. Okay, so all the details there, I guess, as many as we could put in. So that's why I said you can see now if we did opposite orientation, you're still going to get these. You're still going to get this relationship here holding, whether you take outward or inward orientation. Okay, so that's 16.8, and the 16.8 homework is problems 1, 2, 5, 7, 9, 11A. If you have computer capabilities and you want to do parts B and C, that's fine as well, of course, and 13. And I think in an earlier video, I mistakenly said that there are not any verify Stokes theorem problems. And for some reason, when I was looking for those, I passed over problems 13, 14, and 15. So 13 is a verify Stokes theorem. So just remember, when a problem asks you to verify, you can't actually use the theorem. So in particular, you might be tempted to, when doing the curl of f dot ds side, you might be tempted to use independence of surface. You can't do it because that presupposes Stokes theorem. So you have to kind of go the long route on each side. Okay, so that leaves us with section 16.9 on the divergence theorem to go. And that's what we'll do next time.